Okay, then let's start. Yeah, we have to organize still a little bit, especially the topics. Yeah, parallel to the lecture in April, where you should form groups. Ms. Grito, have you some preferences, or could you talk to anybody else so that you can form a group of 2 or 3? Okay, inequality or forecast. And do you have already some partner? Okay, then we will just form somebody. So this one and this one. Within class here, is there somebody who wants to join a group with Miss Creto? Yeah? Yeah, okay. You would like to forecast and your name was Mandland, or? Yeah. Okay, then I will put you here. So maybe it is, if then you form this group. Yeah. Are there other groups? I have already a group with 3 students. They had a preference for this one. Yep, the first two. Okay, so and this was then S and I. Yep, S, I. These two. Yep. Um. Okay, Mr. Frias, do you have any preferences? Pardon? Which one? Inequality. So then maybe here. Then, in case you will form a group with her, and then I just set Mr. Ebeler and Mr. Struss just here. Um, no, nobody is there. Then I just ask you, you can choose some number for the first group here. One between 1 and 10. 6, and you 3. So then they are here. And then Miss Creto, Mr. Frias, who wants? I need a number again. 4. And you again 6 or some number, some other number. Hmm? Again 6. Okay, then let's see. Oops, 10 times. Yeah. Zufallszahl. Open, close. This should work. 1. So I'm sorry. Oh, it's okay. Yeah. Miss Creto, is it okay for you? Not taking the second one? Okay, good. Then this again here, and then you will go here, and but then do you want to join the other ones? Because I need another group of 3. Yeah, because then we are done. And then Miss Wendland and Miss Greto. Okay, you are doing forecast. So, das ist dann das. Das. Hoppala. And Miss Hanno. And this is where is it? There. And Miss Wendland. Oh yeah, 2 times W. Yeah. Yep. Mm-hmm. Only in this week, because I know that here are some students which have problems to join on Tuesday, and we will find then some date where it is possible within this week for you. Ja, also ich frage Sie dann eben, wann Sie können, und vielleicht abends oder sowas könnte auch sein. Ist es okay? Bitte? Within this week of the 28th of April. Ja, also weil ich möchte ja auch, dass genug Studierende hier sind, und wenn wir dann nur zu zweit da sitzen, das bringt dann auch nicht viel. Da machen wir am besten dann einfach eine Umfrage im Moodle-Kurs, und das kriegen wir schon irgendwie hin. Ja. Mhm. Ja. Nee, die beiden zusammen. Die beiden zusammen, ja. Ich kann ja auch nicht zufällig, ich kann ja nicht das gesamte Semester hier einkassieren. Dann steigen mir die Kollegen aufs Dach. Yeah, but the idea is, especially with these topics, that you by your own taking a little data set and doing some data crunching. Because yeah, this I think I already told this to you, that when I studied, that I almost did nothing like this, and then I left university, and what I had to do is look into the data, calculating many parameters and presenting these. Pardon? Pardon? What? Again? You can think of some interesting data then, what you want to do. Yeah, and then we just, yeah, interact, and you ask me, well, I found here a nice little data set. Maybe you are doing within another lecture some project or so, and there you have some data and you want to analyze this. You are quite free what you can do then. Okay, then that's it, and we will go on with the lecture. And so that everybody has more or less the same starting point. Some guys have already participated last semester in this external exam, and they already did the simple linear regression, or in some other courses I within a term paper have the task that the students should do a simple linear regression. Has anybody of you already participated there? There, you should do a regression of economic growth and unemployment. I don't know, because there, then you also have already seen this. So if you have participated there, then I don't know if today I come to the multilinear regression. Otherwise, you have already seen what I'm now talking about. So, because, yeah, quite often in economics, we have the situation that you have one variable and you want to explain this variable with another variable. For example, that you say, well, my profit time series depend highly on my cost situation. Quite astonishing, since profits is revenue minus costs. Well, and here I have also a time series where I say I have, let's say, within the last 22 months, I have the number of a small enterprise, the number of orders, and the value of the accumulated value of these orders. So in the first month, I had 2 orders, and the value of these 2 orders were 36 euros. So on average, 18 euros, and in the second month, 4 orders with an overall value of 44. So on average, this would be 11. So, and this is your raw data. And now you want to analyze it. Well, of course, then you can do what we have already done, calculating averages, calculating variance, standard deviation, and so on. And what is also possible, that you do somehow a graphical interpretation of it, so that we put it just within a 2-dimensional diagram. Then let's do this. Up, up. I copy the data. No, that's not. Where is my example sheet? Here. Oop, this we don't need. And now the linear regression. Let's convert this into vertical data. Yep. And then you have the possibility insert, and here for the graphical representation, maybe you, or hopefully you already know this possibilities, and this is then the XY scatter plot. So, and to know what you are doing, let's go into the data, and then you see here number C are my X values. So order is on the horizontal axis, and column D, volume, is on the Y, on the vertical axis. Then let's also put this on our axes. So this would be then volume in euro. And here we have orders. Yeah, and why are we doing this? Well, we want to have an idea how these two variables are connected. Well, and if we just look at this picture, then we would say, well, very surprisingly, the higher the number of orders, the higher is the overall volume measured in euros. Yeah, and so you have more or less a first qualitative link between your two variables. And what we are now want to do is that we want to have not only this qualitative link, so by just looking at the data by eye, but we want to have some quantitative measure. What we now want to talk about is somehow, yeah, what is, so to speak, a reasonable fit which we can make through the data. So because what quite often we would directly do that we take then our pencil and we draw just a linear line through these data point as best as we think it should be. So just roughly doing this by hand. And now I will show you a concept which we are standard which we use as a standard. But you have also to keep in mind this is then not the best one, or this is not the right one how to do it, but it is just a reasonable way to do it, where we have good argumentations why we are doing it, like I will show you in a minute. Yeah, but it is not the right one and it is not the best one. So what we are now, yeah, more or less doing is somehow to do a decision theory, how to make a good decision. And as we deal with human beings, there is no right or wrong because we always can do whatever we want. Okay, let's put this into my slides. This would be then just the scatter plot. I think you have already seen something like this. So that because I again will go with you through the analysis very slowly and hopefully in a very transparent way. So here we have 22 data points, and again, I will go with you through the analysis just within Excel and in some slow steps. Then I use a data set where we have only 6 data points. Okay, so let's have a look at some company where we again look at the sales volume, and there is one guy or more or 2 or 3 guys in this company. They are driving through Wilhelmshaven and Oldenburg and Jever and so on, and they are just knocking at the door and ask, well, will you buy this product? And then, of course, you can count the visits, the number of the visits these guys are doing, and how much do I sell? And over these 6 years, then I have in 2008 9 visits and a sales volume of 24. In 2009, 11 visits and a sales volume of 33, and so on. Well, and then maybe within this company, you have the idea looking similar to this scatter plot. Somehow I see not 100%, but somehow I see the more visits, the larger is the sales volume. And behind the visits are, of course, some people, 1 or 2, maybe 3 guys doing these visits. And this is, of course, then creating cost in your company because you have to pay them. Or if you are doing this by your own, then you are investing your time. This is also costly. And then maybe you are thinking within your company, oh, I want to grow, so let me increase the visits. But this means for me to invest more time, or let's say to hire a new person. And then you think, well, the maximum number of visits was here 20. Maybe I need another guy to increase the visits to 30. And if I then have only this qualitative link that increasing my number of visits would increase my sales volume, then of course this in general would not be enough for me for a good decision, because if I only quite sure that I increase my sales volume, but if the increase of my sales volume is less than the increase of my costs, then to hire a new person wouldn't be a good decision. So I want to have an idea how much additional revenue will I get if I hire a new person, so that for roughly that I roughly can increase the number of visits by a number of 10 or 15. So what would be, using my historical data, a good forecast? What would it mean if I increase in the next year the number of visits to 30 from my historical data? What would be a reasonable forecast? How much would increase my sales volume? This is what we want to do now from these data. And for this, as quite often doing statistics or doing mathematics, then we ask this little German guy who I think even he was born in Brunswick or in Göttingen. down here in Lower Saxony. Later on, he was a professor in Göttingen, and yeah, this was more or less the starting point why the University of Göttingen is one of the most famous mathematics universities in the world. And maybe you know this little guy. He is called Carl Friedrich Gauss. Maybe the most famous after Archimedes, most famous mathematician in the world. And he has more or less, I think he was then in the end almost 80 years. He has done almost in every topic in mathematics something fundamental. And one thing what he invented is a reasonable linear regression. So what I said to you, what would be a reasonable way to put a linear line through our scatter plot? And yeah, the history behind this is he was then quite famous, and the Earl of this region then he wanted to know, well, how large is my country? So going back 300 years, there were no airplanes or something like this, no helicopters. So it was not so easy. Where are the borders of my country? How long are the distances and so on? And then he sent him out to measure quite accurate the region up here. And he has done this in the way that he put on the landscape triangles. So here was some guy looking in this direction, and there was standing another guy, and then they measured the distance on a line within these two. Mm-hmm. And then he went in a triangle to another point, and then they measured this distance, and they measured this distance. And then in practice, you can think of that theoretically, this should be a perfect triangle. Because in school, you have learned that if you have the distances of the three lines of a triangle, then it is accurately defined. But in practice, you have to measure these three distances, and then you see, well, it doesn't fit. If I go from here within my measured angles, these distances, then I have a little error at the third point. And yeah, he measured then all these data, and then he said, well, always I make some little error because in practice I cannot be that accurate. And then he thought about how should I now change my practical data that in the end I have my landscape that from Brunswick to Wilhelmshaven was founded only 150 years ago, so to Jever. And maybe you went a little bit around this region. Two data points were the windmill in Farel. I don't know if you know this. From there he measured, and the tower of the castle in Jever. These were 2 points where he has done these measurements. And in Jever you can walk up into the tower, and then you see his the way how he has measured this. Yeah, and the way how he has done this is called linear regression, and this is maybe the the mostly used way to do it. And in economics, then we, so to speak, use this as a model to explain one variable with another variable. And we use the linear regression. So the theoretical model behind this is that we say our explained variable y is just a linear function, and this linear function is depending on our explanatory variable x. And now we have data for y and we have data for x. And if we assume that they have a linear dependence, what we have to do is then that we have to estimate from our data the cut of the vertical axis, in this example, this number 3, and the slope. So if we have only the data, our general assumption is that y is a plus bx, and a and b are just some real numbers. Okay. And here some simple examples. If the blue dots and the red dots would be our data points for y and x. Maybe I should have here also y and x. For the red dots, what would be your estimates if you look at it for a and b? Well, I gave you the units on the axis here from 0 to 25 and from 0 to 12. So what do you see? I'm going down 1 and to the right 2. And I created the data like this. It's always the same. Down 1, 2 to the right, and so on. 1 and 2. What would be then the slope? Because I see it's always the same slope. So for red, going down 1 and to the right 2, 1/2, of course. And where will I be then if I put through this a linear line? Where's my outcome on the vertical axis? I would say I'm here at 19, so it would be 20, yeah? And for the blue data points, yep, um, 3 you meant, or no, what you meant now? I need now the slope, B. Oh yeah, this is also great in the internet. Then we can put this together. Let's do this and this for the red ones would be then 20 minus 0.5x. Nice. And now we are going to the blue one. 2 plus 3x, and I think also, is it 2? I go down from 8. 1, 2, 3. I'm here, and great. Here we are. Yeah, because 1 to the right and 3 up. Also always the same triangles. 3 and 1. And then the cut at the vertical axis would be 2 plus 3 times x. So this would be A and this would be B. Well, this is of course very simple because here we are quite happy because fortunately all data points are already lying on a linear line, and in this case then we have to admit we can also say this would be the best fit. I think this is, it would not be very reasonable to assume now another linear line. Yeah. This one, 2 plus 3x, because the slope is 3. Yeah, B is a slope, or have I done something wrong? Oh, yeah, y, sorry. Okay, now I understand. Yeah, thank you. Sorry. Okay, so these are, of course, very simple examples. Then let's go to our data set, which I gave you here. These are these data points, and they look like this. And then let's say maybe this one would be reasonable, maybe this one or this one. We don't know. So we have to have some algorithm, and we have to have a good argumentation which of these many reasonable linear lines we should choose. And let's say which one we should choose. Well, and for this, then we, if we would have the fitted line, then we have the theoretical model. So if we already would have the slope and the cut of the vertical axis, then we could insert into this model our values of our independent variable x, and then we can calculate the data points lying on this theoretical model. And in these two very simple examples, these numbers y hat I directly coincide with the real data. But in general, if we go here, then, for example, I think this was then 9. And if we choose this linear line, then the real data and the theoretical point, due to our model, they won't coincide. And this general difference between the data point of the dependent variable and the assumed point lying on our model our line due to our model. This, very surprisingly, we call just the error. Think of my historical example, going from the starting 2 points with my measurements to form the theoretical triangle. They saw, well, it doesn't fit. We have a little error. And what this little guy Gauss now has done, he said, well, I give you an algorithm how you should vary your slope B and your cut of the vertical axis, how you should vary these with respect to all these errors. Because for every data point you have an error. And he said then, well, you should orientate yourself on the sum of all errors, but similar to this, what we have done in the introductory part, the last 3 weeks. Well, sometimes my real data point will be above my linear line here, and another data point will be below my linear line. Well, and if I now only sum up, again, only all differences, then in general you would just subtract, and maybe then my errors could cancel out. And for this, of course, I want always only to calculate the real value of the distance. But again, with a similar argumentation, why using the square distance and not the real, the absolute value of the distance? Well, the argument was, remember this, that can we can do more mathematics to have a smooth function, and the absolute value has this kink, and the squared difference, I said to you, we find this squared difference in the description of the normal distribution. Remember, squared distance is found in the normal distribution, where we had f of x of the normal distribution is 1 over square root 2 pi sigma squared times e x minus mu over sigma squared. And here you have again this squared distribution. And is still somebody or the guy in who has the topic of a maximum likelihood estimation? This one here. Here? No? It doesn't matter, because this concept of a maximum likelihood estimator, this is also very deeply related to the concept of using as an algorithm to minimize the sum of the square distances. So the guy who will talk about this topic then hopefully also talks about this dependence. And this concept is also related to the maximum likelihood estimation. And actually, Carl Friedrich Gauss, he parallelly developed this maximum likelihood estimation and his concept to measure the country of his Earl. Okay, so now we have this algorithm, and now we want to calculate, well, what will be then given our data set, the numbers for the slope and the cut of the vertical axis in such a way that if we sum up all this one, I think the downward here I had, this is lying on, and this would be then the largest one, that the sum of all these squares would be the smallest area. Well, and something like this you have done in mathematics in school and also here in your introductory course in mathematics. Because what we can now formulate is a function, and this function is now overall depending just on our two parameters a and b, the slope and the vertical cut, the cut of the vertical axis a. Well, and what we want to do is we want to minimize the sum, the squared sum of all our errors. These errors are depending on our linear line on a and b. So this is just yi hat. So we have a function depending on two variables. We know it is a smooth function and it is twice differentiable. What are you doing mathematically if you want to minimize such a two-dimensional function? Hmm? What are you doing if you have a one-dimensional function, f of x? If you know it's smooth and differentiable, what are you doing? Unfortunately, economics is quite open to make calculations. And something like this, in my opinion, you should do in every second lecture. Maximizing profits. You take the derivative, yeah? The first derivative, and what are you doing with this first derivative? Yes, we want this turning point, and what kind of what do you find if we take, for example, f of x is x squared, and the minimum of this parabola is just here, and the first derivative in this minimum is doing what? The first derivative, the tangent is a horizontal line, and the slope of a horizontal line is Hmm? This is just the geometric interpretation of the first derivative. And this you should have, yes, it's just 0. Oh, I'm going just to the right and no step upward. Yeah. So this is then f prime of x equals to 0. And if I have a 2, a 3, a 100-dimensional function, what I'm doing then? 10 years ago, I was really angry about you or your former fellow students. And nowadays, I'm not angry anymore. Because why? We do not explain it anymore to you in school. And this is not good. Because these are the fundamentals you should know. And especially in economics, because in economics, well, in some lectures in microeconomics, you are doing then profits is only depending on quantity times P price times X. This is your revenue minus some cost function, and the costs are also depending on the quantity of your output X. What you are doing then is P prime of X. If you have a fully competitive market, then prices are given for you. You cannot change anything because if you would raise prices, everybody is going to your neighbor and your enterprise is collapsing. So you have to take the price as given. So this would be then the derivative just P minus C prime of X, and these are just then your marginal costs. And your optimum condition is then price equals marginal costs. Well, of course, this is done mathematically. Well, general, we give you then in the exam some function like cost is 2 plus x squared or something like this. And then you have to solve it. But also if you interpret it geometrically, and this should always in behind if you are studying economics, not doing only the mathematical calculation. Because, for example, take a very successful bakery. Is this guy then taking the first derivative in order to calculate the price for his bread? I don't think so. But what this guy from his data sees is, okay, I have revenue. I'm in a fully competitive market. This is somehow similar like this linear function here. So revenue is a linear line with slope price. And what he also then sees is this assumption that in general the cost function is a convex function. So if I have a high production level, that relatively the additional costs will be larger and larger and larger. So it becomes always more difficult for me to produce. And this then means my cost function would look like this. So this is P times X, and this is my cost function. This picture, so to speak, this knows the clever guy. But now he is not doing any derivatives. But then he sees, well, in the beginning, when I'm starting to produce, the difference between these two functions between these two lines is my profit. If I'm now starting to produce, this would mean in the beginning, the slope of my cost function is lower than the slope of my revenue function. So at the beginning, the profits are increasing. So this, and this is then in behind what he then, without knowing, is doing. He is calculating the derivative, because this interpretation is just I'm calculating the tangent on of my function. And then in the end, he sees, well, at some point, this is switching. At some point, the increase of my cost function is larger than the increase of my revenue function. And at some point, when the slope of my cost function is just the same as the slope of my revenue function, after that, my profit starts to decrease. So the last unit I will produce is just the unit where the additional cost equals the additional revenue. Well, and this is just what you have here. Price equal slope of cost function. Slope of cost function is the additional cost of the next produced unit. And so this is my general optimal condition. Okay, well, I went to something else, but well, since we find this almost everywhere in economics, these interpretations of calculating the first derivative and setting this to zero, but behind there should be always a general argumentation why this is a good concept. Okay, but now we have a multi-dimensional system, and in general, my profits will not depend only on one variable, not only on quantity, also on input prices and whatever. And then we open our concept, what you have learned in school, where you have only mostly you are looking only at one-dimensional system. Then 200 years again, this little guy Gauss was also involved creating all these methods, and then given some assumptions that in general you have a smooth function and differentiable and so on, and then you can say all partial derivatives have to be simultaneously set to zero. Well, again, in microeconomics, you have done this when you have done, for example, your utility maximization. There, in general, you had one, even three-dimensional function, depending on your quantities of your two consumption goods and this crazy Lagrangian multiplier. And this was then maybe a function who has looked like square root of x1, x2 minus lambda times 1000 minus 2x1 minus 5x2. And what you have done then is you have taken the derivatives with respect to x1, the derivative with respect to x2, and in general also the derivative with respect to lambda. But this derivative you already know because this is just your condition you have used in order to construct this multi-dimensional function. Well, and now for a minute we just forget about these economic interpretations. We just say, well, we have here a two-dimensional function and we just take the two partial derivatives of this function with respect to a and b. So df with respect to a. Well, and the last 2 weeks, I told you that within this course, you should also to start, and you will see it if you look at your personal topics, that you have to deal with these signs, these summations. Well, what does this summation mean? This means y1 minus a plus bx1 plus y2 squared a bx2 squared plus until yn minus a plus bxn squared. So what is then the derivative of this function with respect to a? Well, I have to look where do I find in my function the parameter a. I find it always in the square brackets. These are all constants. The derivative of a constant is 1. Think about it. F of x equals 3. What is f prime? 0. Huh? Because f of x equals to 3 is just a horizontal line at the level of 3. Okay, so all my data points of y are vanishing, taking the derivative, but then I have to calculate the derivative of this square bracket, and I find the a within the square bracket. So what kind of rule taking the derivative I have to use? When a function is within a function, then I have to use the chain rule, of course. So this means I take just the outer derivative. I'm looking only while there's a square. The derivative of a square is 2, and then what is inside. So I have then 2 times a plus b times x. And the inner derivative here is quite easy. What is inside the bracket with respect to a? Oh, bx is, if I look only at a as a variable, I have to treat it as a constant. Again, so this part, the derivative, is with respect to a, 0. And a with respect to a, the derivative is, now you can use what your fellow colleague has written. This is 1. F of x equals to x, the derivative is just 1. Yeah? So in general, I have to write here times 1, or I can leave this one out. Well, but I find it, oops, for x1, for x2, and so on, always. So what I have here is then xi, and I again put the summation sign in front from I to 1 to n. And what I always have to admit, I have left it out. Here I have a minus sign, and here also. So in front of all, I have a minus. So, and then I also, or then we have, this is 0. Then I know if I have inside my summation sign always the same constant, I'm multiplying every part of my summation with the name number, I can take it out. So this would be that, this would then translate into sum I to 1 to n a plus b xi is just 0 because I can divide both sides by minus 2. Okay, let's take the derivative with respect to b. Let's maybe take this in red. Again, we can use this representation because I know you haven't done quite often it directly with these summation signs. So let's go again, go through it slowly. Yeah, great. We have to do exactly the same. These are again all constants, the y. I have now directly the minus in front of all, and I have just to take now the derivative of the inner bracket with respect to b. The a's are all now constants for me with respect to b, so they cancel, they vanish. 0 is the derivative. And now I have to just switch. And this is sometimes a little bit hard for students because in school you always have learned the variables x. But now we switch the variable which we should look for our derivative is not x but b. So b times x, the derivative with respect to b is just x. So the sum 2 I equals 1 to n a plus bxi. And now every time also times my x1, x2, and so on. So here x I equals to 0. Ah, Quatsch. Or no, that's right. So dividing by minus 2 is xi a plus b xi is 0. Well, and what I now have here is this and this. If I multiply this out here, then I have axi plus b times xi squared. But with respect to my variables a and b, it's still a linear equation. Because if I look at a and b here, a and b here, there is no exponent. It's just to the power of 1. So these are two linear equations in the variables A and B. And this, well, my oldest son is now in class 12, and I have seen that they still have done this. Just a system of two linear equations with two variables. This we know in general, we can just solve it. And there we have a solution mechanism. And again, if you have not only two variables, but 8 variables and 8 linear equations, then you have to do this stepwise. And in the end, you had this triangle. And what a surprise, this is called the Gaussian algorithm. Again, this guy has created this. So this is in general solvable for A and B. Well, you have, if you look at this from a theoretical point of view, you have to be a little bit careful because there are some special cases where you do not have a definite solution for A and B. So it can be possible that it is not solvable, and it can be possible that you have infinitely possible numbers for A and B. But these are only special cases. In general, we can solve it definitely for A and B. And what you, and this I will not do with you, you can show in this case that you have always a definite solution for A and B. Okay, this I put here again for you. And the outcome, this we have already done. Oops. The outcome looks like this. It looks a little bit messy, but in the end, it's just the solution of a linear system you have here. And if we again look a little bit more careful into the formulas, then we see here for A, we have just the sum of all xi's and the sum of all yi's. If we would simultaneously divide both of these numbers by the number of our data points, what again would we have? Just the arithmetic means of x and y. Here again, more or less the arithmetic mean. And here, the sum of the product of all x and y's. What is this? This dividing by n is just the arithmetic mean of all products of x and y. So also interpretable numbers. They are, at a first look, it looks quite awful, but if you have a deeper look into these formulas, then it is not that awful anymore. Or here, this is then just the arithmetic mean of all squared x values. And this is the square of the arithmetic mean of x. And for b, you have it quite similar. Again, if we look at this product of both numbers, this would be then the arithmetic mean of the products minus, oh, this is wrong here, sorry. This has to be x bar times y bar. So not a bar, just simultaneously on both, but first the bar. So this means first taking the arithmetic mean and then multiplying these two numbers, because this in general will be another number than first multiplying and then taking the other arithmetic mean. So these two operations do not commutate. You cannot interchange them in general. And here also first taking the square and then taking the mean. And here the other way around. First taking the arithmetic mean and then squaring it. And what also then can be shown is that A, if you have calculated B, you do not have to use this formula, but you can then just take the arithmetic means of your two data series, taking this calculated B, and then you can directly calculate A. So what does this also mean? A times equals this also means directly y bar is A plus B x bar. And this is also a quite nice result. And this is also where we then can argue the method we have chosen, minimizing the squared distances in order to obtain our linear regression line. Because if we are doing this, this is true in general, and this means that always the data point of the arithmetic means of our two time series lies automatically on our regression line. And maybe intuitively for you, you say also that this is a quite nice result. Because in statistics, what we are very often are doing, if we have a data set, the first thing what we are doing is calculating the arithmetic mean. That we say we have 100 data points, and then on average, the income of these people is 1,200 euros. This we are more or less, this we are doing without thinking about it, because it is so intuitive that it is a reasonable way in order to describe a data set. And then on the other hand, doing the linear regression has the outcome that these two representatives of our two data sets for y and x is also lying on our regression line. So this is then, so to speak, also a nice result where we can say, well, this fits our intuition that this should be the case. Okay, then we can also, give something else. Well, since we have here two time series, y and x, and in the beginning of the lecture, there we have calculated the variance of one series or one data set. This was just the squared distance of these numbers with respect to the arithmetic mean. But now we have a two-dimensional problem. And since we have this two-dimensional problem, then we can also think of something like a simultaneously measure for the variation of both time series. And this variation measure is also defined quite intuitively, that we just say, well, we calculating not the square distance, but we calculate the product of both numbers or both variables with respect to their arithmetic mean. So xi minus x bar times y minus y bar. And we are making some normalization since we have chosen that, or no, we do not make a normalization in this case later on. But then this variable we call then not the variance, but the covariance. So some number, and look at it, this can also be minus. Yeah, since these two numbers can be negative. So this is, so to speak, a simultaneous dispersion measure. And dividing this by the variance of x, this also can be shown that this is directly related to the slope of our linear regression, that the outcome is also the slope here. Okay, well, I have talked quite a lot today. 3 minutes left. Do you give me today 5 minutes overtime? Yeah, because then we are just go through the linear regression because we have now everything together. We know what we have to do, and now we are just calculating the slope and the cut of the vertical axis of our data set. Oops. So if we are going into our formulas, then of course we know we need the arithmetic mean, so the sums of our data points. We need here the sum of the squared x's, and what we also need is the sum of x times y. Then let's do this. X times y and x squared. We need always the sum of these points. And then we go inside here, and for b, we, or the means, we also, oh, let's go here. So we have 6 data points. Oops. So, and what should be b? B should be n, so 6 times the sum of the multiplication of x and y equals, oops, 6 times xy, 2134, minus the sum of x, here we are, minus the sum of x times the sum of y. So minus sum of x is 70 times 162. divided by, again, 6 times the sum of the squares of x, 6 times the sum of the squares, 940, minus sum of x, 70 squared. This is b, and a. For this, for simplicity, we can just use this formula. At first, we need the two arithmetic means. So x up, arithmetic mean of x is 11.6 and 27 for y. So a is y bar minus b times x bar. So equals y bar 27 minus b times x bar 11.6, 3.9. Well, this is more or less now done by hand, but I think for the first time it is also quite useful to do it once in this very slow way. Because of course we have formulas here, and b is slope, and in German, what is slope? Not our international students, but Steigung. Yes, so Steigung, we have the formula here. In your English Excel version, it will be slope, I think. And then using the y data, semicolon, oops, until this, zack, and using the x data, enter. Ah, great, it's the same value. Well, and the cut of the vertical axis in German. Any idea? Abschnitt, genau, but unfortunately it is not Abschnitt, but almost. It's called Achsenabschnitt. And again, feeding in the y values and feeding in the x values, we have 3.92. And that's it. So what do we have? We have 198 and 392. Which one was which? This one. 198, 392. And let's also copy these numbers here. And the sum were 70, 162, 2134, 1940, and this was then 6 times, where is it? I do not have it in my hat, xy, minus 70 times 162 over 6 times 940 minus x squared 70 squared. And the mean, arithmetic mean was 11.6, and this was, I think, 27. So A was y27 minus b198 times x bar 11 period 6. 5 minutes. Thank you very much for today.